Alright, we're going to start off by reviewing the intermediate value theorem. This theorem states that if a function is continuous on a closed interval from a to b, and y is a number between f of a and f of b, then there is a number, x equals c, in the open interval ab, such that f of c equals y. It sounds a lot more complicated than it is. Let's say we're given this graph here, y equals f of x. For some value a, we have the point a, f of a. Some value of b, we have the point b, f of b. If we can choose any value for c between these 2 points, we know that the corresponding f of c value will lie between these 2 points, f of a and f of b, and along this curve that I've just drawn in red. It's a lot simpler without all the complicated words. Let's move on to our first example. Given the equation y equals x whenever x is less than or equal to 0, and y equals x squared whenever x is greater than 0, let's see if we can show that there is a value x equals c such that f of c equals 0. Well, we just reviewed intermediate value theorem, so let's try and prove it that way first. For that to be true, we would need to prove that this function here is continuous at x equals 0. So, if y equals x and x equals 0, y must equal 0. If y equals x squared at x equals 0, y equals 0. 0 equals 0, and cha-ching! We've proven that the function is continuous at x equals 0. Therefore, we know that both of these functions are continuous on their own. So, as a whole, this equation is continuous. We can use the intermediate value theorem to say then that there must be some value, x equals c, such that f of c equals 0. Pretty simple, pretty nice and easy. Let's move on to our next example. Technical difficulties. Alright, for the equation given, show that there is a value x equals c such that f of c equals 5. Well, this is a kind of nasty looking equation to start with, so let's try and simplify a little bit. We can factor this cancel out these factors, and we're left with a nice simple equation, y equals x plus 3. For visual sake, let's graph this for a second. Now, the one thing we do have to keep in mind is that we crossed off a product here, which means that we have eliminated a value. There is now a hole at x equals 2. If x equals 2, y equals 5. So the hole is at 2, 5. There is our new graph for this equation. Let's go back to the question now. For the equation given, show that there is a value x equals c such that f of c equals 5. Well, we can't. There's a problem. This function is not continuous at x equals 5. Therefore, the intermediate value theorem does not apply, and there is no guarantee that there is a number that will satisfy that.
Hello, we are going to talk about the extreme value theorem, which states that if f is continuous on a closed interval, then f has both an absolute maximum and an absolute minimum value on that interval. We're going to first look at this graph, which is a graph of f, which shows a continuous function on a closed interval, and we can see that's a closed interval and continuous. And there is a minimum, an absolute minimum, and an absolute maximum value on this graph. the absolute minimum value is quite clearly right there because it's the lowest. And the absolute maximum value is on an endpoint at B. So that's right there. The absolute maximum can be on an endpoint or amongst the function in the middle. Now on to the second graph that I have here. We have a discontinuous function. It's discontinuous at Q. Now we cannot guarantee that there is an absolute maximum and an absolute minimum because the theorem states that it has to be continuous and on a closed interval. Well, we have a discontinuity there, and there can't be an absolute maximum because the points can get infinitely close to that point, but there is no actual maximum value. It's not clear, and it can't be that because it's lower than that. There is a minimum, but there is not both a maximum and a minimum, so it doesn't follow the theorem. Now, example 3, we have h of x equals the natural log of x plus 1 in the domain 0 to 3. It's on the closed interval 0 to 3. Now, we can guarantee that it follows this interval because the natural log of anything positive and not 0 is going to be continuous and exist. So we know that because the domain is 0 to 3, so if we plug it in, we know it's the natural log of numbers on the closed interval 1 to 4. So we guarantee it's continuous, and we know it's a closed interval because it's given in the domain. So it follows this theorem, and we can use that to know there are maximum and minimum values, and we go on to find that the critical values are 0 and 3 because those are the points where h of x equals 0 or h of x doesn't exist. And we go on to find the minimum and the maximum values of 0 and 1.386. Okay, and this way is much more effective. Finding the critical values and using this theorem is much more effective than taking the derivative of that and trying to find taking the derivative of that and finding the values of the minimum and maximum using first derivative tests and maybe second derivative tests. It's just more efficient. We're going to talk about the mean value theorem, which states if a function f is continuous on a closed interval ab and differentiable on the open interval ab, then there must be some value c between a and b such that the instantaneous rate of change at c is equal to the average rate of change from a to b. So in simple terms, that is saying that f prime of c, or the instantaneous rate of change, is equal to f of b minus f of a over b minus a, or the average rate of change, on a point C between points A and B, if and only if f is continuous on the closed interval AB and f is differentiable on the open interval. So our graph here shows we have our f of x function, the black, which is, okay, and we have the function f of x, and we have the average rate of change in blue, and the theorem states, because it's on a closed interval, continuous, and differentiable on the open interval, that there is definitely one point on the function that is equal, that the instantaneous rate of change is equal to the average rate of change. And that's at point C. As you see, the slopes are the same by showing that they're parallel there. Okay, so our second example, we have let g of x equal x to the third plus x squared minus x. And it wants us to find the values on the closed interval -2, 1 that satisfy the mean value theorem. So we know that g is continuous on the closed interval -2, 1, and g is differentiable on the open interval because it is a cube root function, and we know that it takes the general shape of a cube root function. So the mean value theorem definitely applies, and to show the point that it equals to show what value we have the instantaneous rate of change equal to the average rate of change, we use this equation, plug in our values. We're solving for c, which is the point, and which is the x value of the point, and we're plugging in our a's and b's into this formula, and if we FOIL that out use the quadratic formula, we get c to equal 1 plus or minus root 7 over 3.
Here we go, we've got a car driving down the highway. It goes through a 60-mile stretch from point A to point B in 30 minutes. The speed limit posted is 90 miles per hour. Did this car drive lawfully the entire time? Let's find out. Mean value theorem must apply because the car, if you were to graph the car's velocity, the graph would be continuous and differentiable. The car cannot suddenly change velocity in any way. So, if mean value theorem applies, there must be some point in which the average rate of change is equal to the instantaneous rate of change. The instantaneous rate of change is the speed that you would see on your speedometer. Well, looking at this and this, we can say that the average rate of change is equal to 120 miles per hour. If, at some point between A and B, the instantaneous rate of change must also be 120 miles per hour, then the car did not drive lawfully because they were going at least 30 miles per hour over the limit at one point.